Final liquid property we want to talk about is capillary action. So capillary action is the tendency of liquids to flow in opposition of gravity through narrow spaces. Okay, so this kind of chart, it's showing a glass that's just water with red food coloring in it. But this would be the surface of, say, the large container with respect to gravity, right? There's water, you poured water in there. And you will note that this is a pretty wide opening. We have some smaller openings here. And you can see that as those openings get smaller and smaller, the liquid level is actually going up. And so the water appears to be flowing up these glass tubes, moving in opposition of gravity, right? It's flowing vertically. This isn't due to water pressure necessarily, some sort of push from this right here. That would have just, that sort of pressure would mean they'd be all at the same height. But we can see as the glass gets more and more narrow, you can see there's fainter and fainter red because it's more and more narrow. It's going vertically up. This is a computer generated image, but you can use this if you've ever dyed flowers or bought some exotically colored daisies. That's how they do it. You can get that water flows up into plants. Capillary action is how all water flows up into plants. Very, very important idea of how you get water from, say, the ground up into, say, 100-foot tall tree, up into those tops of those leaves. Water's making it up there, and capillary action is the driving force. So very important biologically. And the driving force of capillary action is made up of two components that we can understand at the molecular level: cohesion and adhesion. Okay, and so cohesion, you can see hesion is in both of these words, and adhesion means like sticking together. And so if you think of that's like molecules sticking together with each other. So cohesion is attraction between identical molecules, and adhesion is attraction between different molecules. So a group coheres together, whereas, a piece of tape adheres onto a surface. It sticks onto something else. And this is actually why water forms a meniscus in, say, a graduated cylinder. It's based on cohesion and adhesion. So if we look at, say, the surface of water, we have our water molecules, those blue spheres. And so the cohesion is, we know that those molecules are held together. And cohesion comes from the intermolecular forces we've talked about so far. The idea that water molecules want to be close to other water molecules. So now adhesion is the idea that there is an attraction between different types of molecules. Okay, so in the case of water in a graduated cylinder, the water is attracted to the glass. It is still the same ideas of polar dipole-dipole interactions. It's just a little more complicated, but it's basically water is polar, glass is also polar, and so they're attracted to each other. And so what ends up happening is that all these water molecules are attracted to the atoms in the glass, and they are literally pulled up. And so they are attracted towards us. They are literally pulled up in opposition of gravity. And cohesion says, so this, say, water molecule is attracted to the glass. Well, these other water molecules behind it are attracted to those water molecules, that water molecule. And so it's this kind of chain where the molecules are getting pulled up, and they come from the bulk. It's not just the surface. They're getting all pulled up along the glass. And so this cohesion says that the water molecules are attracted to the glass. Adhesion says that those water molecules are attracted to each other, so they just get kind of pulled along in a chain. And so that's why in a graduated cylinder you see a meniscus. And you can see a meniscus would happen, like a beaker still has this sort of cohesion or adhesion pulling water molecules up. It's just the surface is so wide you can't see it. When they're narrow, you can see that sort of curvature that comes from it. This idea of adhesion, that you have two different compounds, whether or not they're attracted to each other, is going to depend on what the two compounds are, and importantly, what their intermolecular forces are. So if you have compounds with similar polarity, they're going to have stronger adhesion. So for example, Water, very polar. Glass, also polar. Molecule, atom is it's a polar compound. And so those water molecules are attracted to glass. And so that's why they slide up the glass tube. That's why you get that capillary action. If you had a nonpolar liquid, so mercury is a common nonpolar liquid, and say like a thermometer, and so it would go down, because it's not interacting well with the interaction of the glass. That's why if you think about if you think of like a thermometer, the top of, say, the red liquid, or if you use an old school mercury thermometer, a silver liquid, is rounded down. It's the opposite curvature of a water meniscus, but it's the same idea. It's the same curvature that comes from the same idea. Basically what ends up happening is the mercury is more attracted to each other, and what happens is they kind of, if you had like your tube right here, they're attracted to each other, and so they pile up. So they kind of are piling up. They're more attracted to each other than to the glass. So they avoid the glass and they pile up like that. But there's this idea. So this is one of the things, these interactions between different molecules, we can see is still mediated by their polarity, which we're going to keep talking about as we move forward. And so we can also see that, for example, this also affects how water, and are not just liquids inside glass, but water on two different surfaces. So we talked about the ideas of surface tension, and the idea that we know water tends to form droplets that look something like this. And this would especially be true in the case where the water doesn't have a strong adhesion with the surface that it's on. Because we've talked about surface tension as water just making new surface with exposure to air, where there's an absence of molecules. But there's also a question of what is the surface between the water, or what is the surface area between the water and whatever it's on. So if, say, you put water on wax paper, that is a very non-polar compound, and so you get really, really sharp bubbles. Whereas if you put water on glass, or this is an experimental material that's over here, that's very, very polar, you can get this really kind of flat water shape. So that shape of the water is driven by surface tension. You can still see there is some vertical nature to it. The water still does want to have some sort of kind of piling up, but it is willing to spread out, because you're increasing not only the surface area of the water, which is not good energetically, but you're increasing the attraction of the water with this surface, which in this case is very, very polar, especially relative to glass. But glass still does the same thing. So you can do this at home, put water on a piece of glass, the drops will get really flat relative to water on wax paper, where they're almost perfect spheres. Okay, another video with no participation questions, but one video left in this set, and there may be a question in that video. Who knows? Got to watch it to find out. I'll see you there.